So we had been looking at image compression and GIF and JPEG and PNG. And you need to know the differences between those formats and what they're good for, in what situations which one is best, so that you can make the right choices. To complete the picture, today we're going to look at video compression. Now, you probably will have less call for putting, well, I don't know, we don't know how the word's going to turn out. But certainly at the moment, if you're doing stuff for the web, you don't do as much video. And you have a tendency to just put the video on YouTube and then let YouTube worry about it. And if you're going to put it on your website, play it from YouTube. So it's a very common approach. And there are two main things to consider when you're putting video on the web. Remember when I talked a bit about progressive coding and how you can see some of it before it downloads fully? Obviously for a video that makes much more sense. So a video is going to take 20 minutes, say, to download. If it's a movie, it's going to take 20 minutes. Depending on how it's coded, the viewer may have to wait the full 20 minutes to download the whole file, and then they can start watching it. It's much better, for example, if they wait 5 minutes and then start the movie, and it keeps downloading in the background, and as long as they don't catch up with the download. So if it downloads faster than they can watch it, then they'll never run out of movie. So there are all sorts of different techniques and things you can do in the way you code the video to make it more streaming friendly. We're not going to look at those today really. We're just going to look at the basic principles of how video is compressed. I find it really interesting. I think it's one of the cleverest things I've encountered in computing, in computer science. I'm sick I didn't invent it because I think it's so clever. So for our purposes, when we're thinking about video, we're just going to think of it as a sequence of images one after the other. So you have a picture, then you have another 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 picture, and then you have another picture, and so on. And provided that you have 24 or 25 frames a second, you have the illusion of motion. Animations, cartoons, often go as low as maybe 12, 13 frames a second. So depending on the context, you can kind of get away with it. In a cartoon, if you've got, say, 13 frames a second and the camera isn't panning, it's okay. But if the camera pans across some, landscape, it starts to look a bit, you do notice. I should warn you that once you know how video compression works, you will see things you didn't see before, and you'll become much less tolerant of poorly coded video, because you'll actually see things you didn't see before. So you might end up having to pay for a Netflix subscription or something rather than endure your torrents, whatever. So we're going to imagine, for our purposes, that video is one frame after another. So one picture and then another picture, then another picture, then another picture. And in fact, that's one way you can code video. If you've got 500 frames, 500 images, just have 500 JPEGs one after the other. That's one way to do it, and we call that motion JPEG. So that is one way to do it. But of course, we can achieve some major compression by exploiting the redundancies between one frame and the next. So the first thing is that video is big. So if you were to have video at 640 by 480, which is no great shakes at all. I mean, 640 by 480 is as small a dimension, as small a frame as you'd be prepared to tolerate, really. YouTube does slightly less, and it shows. YouTube is slightly smaller Oh no, I think YouTube is 640 by 480. I'm not sure. How big is a YouTube video in terms of pixels? Don't you even know? Anyway, 640 by 480 is no great shakes. At 25 frames per second and at 24 bits per pixel, you'd be talking about 21 megabytes per second. So that's not very practical. You certainly wouldn't want to be watching your YouTube videos and paying roaming fees on your mobile phone at those kind of rates. So at those rates, video is difficult to store or to process or to deal with. Now, when I started giving classes on this topic, I would have said it's impossible. But actually you can get machines that can handle those kind of data rates now and be happy enough with it. But it is a bit bonkers. So compression is, if not essential, certainly desirable. There are two ways then that we compress video. There's intra-frame compression and inter-frame compression. So intra means within, okay? So if you shift someone in the class, that's intra-class shifting, right? If you shift someone in a different class, that's inter-class shifting, okay? Intra, inter. So intra-frame compression just works at a single frame, takes a single frame of video and worries about compressing that down. And it does that pretty much like JPEG. We don't reinvent the wheel for intra-frame compression. It's like, here's one we made earlier. We do have JPEG in the arsenal. So at that intra-frame compression level, you're pretty much looking at JPEG. Inter-frame compression takes a bunch of frames. So you might like take 15 frames or 20 frames and say, as a group, we're going to compress this group of frames. So a whole bunch of them as a collective, as a set, and you compress that down. And that's much more effective because it turns out very little changes between one frame and the next in video. So if we take, now I've exaggerated this somewhat by actually taking not subsequent frames, but frames that are very far apart. So these frames are maybe one or two, maybe a second apart. And so you notice that very little has changed between one frame and the next. Surprisingly, a lot has changed actually. I'm surprised how much of the background has changed for some reason. But very little changes between one frame and the next. So in 1/25th of a second, even less changes. Because let's face it, if you got a completely different image every 25th of a second, your head would explode. You couldn't take that in. So very, very little changes between one frame and the next. And the idea behind video compression is that you only code the differences between one frame and the next. So if you take the background there, I guess this is meant to look, this is, I guess, a photograph of Dublin or something. That doesn't really change. So if you're transmitting video from A to B and the receiver has already got frame 1, so the receiver has this picture, why would you bother sending the background parts again? And so what the transmitter says to the receiver is, look, you've already got those bits there. You've already got those parts of the image. So just copy and paste those from frame 1 to frame 2 and you'll be grand. Now, here's the bits of frame 2 then that you don't have. Here are the new parts. I'll give you those. And so that's the basic principle behind video compression. Does everybody get the idea? So if you've got one frame, you only send what you need to make the next frame from the previous frame. What I've done here is I've just in Photoshop highlighted the parts that have changed. And you can see that, you know, very little has changed, in fact, between one frame and the next. So all we're interested in now is efficiently describing the parts that have changed between one frame and the next. So all we're doing is saying, you have this already. If you want to make this, you're going to reuse those parts there in the background. The thing is that if you were to address them pixel by pixel, if you were to say, well, this pixel has changed, and this pixel has changed, this pixel is the same, this pixel is the same, this pixel has changed, this pixel has changed, the addresses of the pixels would be so long, they'd actually be longer than the data would have been in them. So we don't do it on a pixel by pixel basis. We break it up into blocks and do it on a block by block basis. So we basically say that the current frame can be constructed by copying and pasting the parts from the previous frame, and then by sending the parts that have changed. So if we look here, the area that I've marked in red, that hasn't changed between one frame and the next. So between frame 1 and frame 2, that red area hasn't changed. And the part in the blue area, that has changed. So we only need to send the blue part. So if the receiver already has frame 1, the transmitter has already sent frame 1 to the receiver, and the receiver has frame 1 decoded and sitting there, then the transmitter can say to the receiver, okay, to make frame 2 now, the top bit and the bit down there on the left, I want you to copy and paste that from the frame you already have, and then here's this blue bit, that's the rest of it. And so instead of sending the whole of frame 2, all we've sent is the new parts that you need to make frame 2. And that's obviously a lot smaller. And so that's the way that's implemented. We're actually going to be talking only about the same thing the whole time, but the way it's achieved is quite clever and gets a bit complex. So interframe compression, we're saying frame 2 is the same as frame 1, except for these small changes. Frame 3 is the same as frame 2, except for these small changes. Frame 4 is the same as frame 3, except for these small changes. And so coding the difference between the frames needs a lot less data than coding each frame one by one. Y'all with me so far? Don't worry, I will lose many of you by the time we're done. No. So we can't address the updates pixel by pixel. So we do it block by block. So basically we break the current frame up into blocks. And we compare each of those blocks with the same block in the previous frame. And if it's the same, or even if it's close enough, we'll say, yip-de-doo, you don't have to do anything with that one. And then if it's different, we send the new block. So in this case here, the blocks in orange are the ones that would be sent. And the blocks that are just in black there, they're left unchanged. So instead of sending however many blocks that is, that's sending only about maybe a fifth of them. So we do it block by block just because it's more efficient. It's not practical to go pixel by pixel, because to address a pixel just takes too much data. Now, this now is where it starts to get really, really clever and really, really hairy. So let's look here at the current frame and that fourth block there, the fourth last block. So if we compare that fourth last block with the same position in the previous frame, we see it's completely different. So you might think, well, okay, we're screwed, you know. So we're going to send that. We're going to just have to send that block. But if you think about it, and this is the really, really clever part, if you think about it, the information that's in that block is in the previous frame. It's just moved. So it is there, it's just not where we were expecting to find it. So it's not like, say, the house or the tree that's in the same position. Because the car is moving, the fourth last block is different. That block in orange there in the current frame, when you compare it to the same position in the previous frame, is different. But the information that we're looking for, the information that we want in order to make the current frame, is in fact in the previous frame. It's just moved around a bit. And so there's a technique called motion compensation, where the video compression algorithm searches around for the missing block so that it can be cut and paste. And so you end up saying something like, this block hasn't changed, this block hasn't changed, this block hasn't changed. You know, no change, no change, no change, that's grand. This block, you can find that in the previous frame, but not where you were expecting it. Go where you were expecting to find it, and then it's like 20 pixels over and 90 pixels up or something. And so you give the location of the block in the previous frame that has the information that you're looking for to make this block in the current frame. I'm going to pause now and let your brains process that for a second. Okay, nobody collapsed. No. But any questions on that? So we're reusing blocks from the previous frame to make the current frame. And if they've moved, we basically track them down and reuse them anyway. So if you're not clear on some of that now, ask me a question, because it's going to get even madder. So, this notion that you can do motion compensation, that only holds if certain things are true. So if objects move in a plane that's parallel to the camera plane, so if things move, you know, this way and this way, South Park style, right, then everything is going to be fine. If things turn, if there's rotation, you know, well then it's not so good. If you're zooming in and out, well then again, it's not so good. Now you must remember, even if there is rotation and zooming, in 1/25th of a second, you know, how bad can it be? Can't be that much. But some things would lend themselves more to motion compensation than others. So I mean, South Park is just a compression algorithm's dream, do you know? Because the characters are flat and they even walk this way, you know, and, you know, they probably have, you know, 10 frames a second, I don't know, maybe even 5 frames a second sometimes looking at it, I think. Whereas, say, you know, The Matrix or something with a lot of explosions, you know, worst case scenario. In fact, there were problems with some of the Matrix DVDs when they came out first, because it was just too much data for some video players to handle. Also, the illumination needs to be uniform. So if the car was to drive under a street light, it was to drive from light into dark or light into, you know, dark into light, well then it's not going to work so well. Or if the light is changing from frame to frame, you know, if there's like strobe lights or disco lights or something, again, that's not going to work so well. And of course, a big problem is if one thing is hidden by another. You know, I mean, if I move out of the way and turns out there's a rabbit sitting on the chair behind me, well, I mean, good luck trying to make a rabbit out of bits of my shirt, like. You know, it's just not going to happen. But in general, at the 1/25th of a second scale, very little is going on. You know, there's a lot going on overall. But from one frame to the next, that's such a tiny time frame that, you know, most of these things hold at that scale at least. And so this is possible. No, so MPEG then is an ISO standard for video compression. So flush with enthusiasm from the success of JPEG, the compression brains decided that, do you know what, we should try and do the same now for video and have a standard format for video compression. Because in the early days, video compression was all over the shop. There was like a multitude of standards, and you see, pre-internet it wasn't such a big deal, because if you were building a system and giving it to a customer, well, you had control over everything. So you could, you know, compress the video any way you wanted, and just make sure that the playback machine had the decompression schemes also. But of course, with the internet, that wasn't going to work. You couldn't have everything deployed everywhere. So MPEG uses intraframe compression. They're called iframes, and it has predicted frames. We call those P frames. And so P frame uses information from an iframe. So basically, if we look at frame 1 there, that would be an iframe, an intraframe, which is basically like a JPEG. So you're saying frame 1, here's the picture. Frame 2 then is a P frame, and P frames use a previous iframe or P frame as a reference. So here we're saying, well, frame 2 is the same as frame 1 with just some small changes. And frame 3 is the same as frame 2 with some small changes. And frame 4 is the same as frame 3 with some small changes. I think my arrows here didn't survive the translation from one presentation software to another. No, you can't keep going like that. You do eventually have to say, okay, did a great job there now, lads, but now we have to start again now. So here's a new iframe. So typically you have a new iframe every maybe 15, 20, maybe you could push the boat out 30 frames, depending. You get some software as well that'll actually detect if there's a scene change, and then there's a need then for an iframe. But you can't just keep going. You know, you can't start a movie and just say this frame is the same as the previous one with these changes, this frame is the same as the previous one with these changes, and keep going. You know, you do have to start again every so often. We call those iframes. You sometimes see them being called keyframes. So sometimes if you've got compression software, it's asking you how often do you want your keyframes? When do you want the keyframes? So if you do any kind of video compression, you see this in the different options. The options may start to make more sense to you now. So frame 1 is an iframe. Frame 2 is the same as frame 1 with some small changes. Frame 3 is the same as frame 2. Frame 4 is the same as frame 3. Frame 5, you start all over again. Okay? Frame 6 depends on frame 5. Frame 7 depends on frame 6. Frame 8 depends on frame 7, and you start again. Now, here's now where it starts to get mind-blowingly clever. Here we have frame 1, frame 2, and frame 3. And here we're looking at the second last, in frame 2, the block in the second last row and second last column. So that one in orange there. If we look at that block in frame 2, and we look at the previous frame in frame 1, it's not the same. So you might say, okay, well, we've seen this scenario before. We're just going to have a look around now to see if we can find that information in frame 1. But it's not there. It's not like that the tire has moved or something. It's just that piece of information that frame 2 needs is simply not in frame 1. So again, you might think you're going to have to say, oh, well, we tried, you know. We'll just have to send that block to make frame 2. But here's the really, really clever part. Yeah, like it's not in frame 1, but it is in frame 3. So the piece of information that frame 2 is looking for isn't available in frame 1, but it is available in frame 3. So imagine if you had a system that allowed you to copy blocks not only from past frames, but also from future frames. Then you could be making some real savings. So in order to code frame 2, we're going to say to the receiver, here's frame 2. A bunch of these blocks haven't changed. They're all the same. This block here, that's not available in frame 1, but if you go to such and such a position in frame 3, you'll find it there. It's the point where people's heads usually explode. So frame 2 is going to be made up by copying and pasting some blocks from frame 1 and some blocks from frame 3. And you could see how successful that might be. You know, most of the information is going to be there, even uncovered backgrounds. My arrows now are all over the shop. So frame 2 is going to use parts of frame 1. So you can see there the green block in frame 2 is copied from a part of frame 1. But the orange block in frame 2 is going to be copied from a part of frame 3. Constructing a frame by copying blocks from both past and future frames is called bidirectional prediction. And so we call those B frames. So we have P frames, well, we have I frames for intraframe prediction, they're just the standalone frames. We have predicted frames, P frames, and now we have bidirectional prediction, or B frames. So if you're in an interview and someone says to you, do you know anything about video compression? And you say, yeah, I know a small bit. They'll say, what's the difference between a B frame and a P frame? No, not many people know this stuff. I mean, so you will. This does create some problems, and I hope now my arrows haven't let me down here. So if we have frame 1, okay, that's a standalone iframe. And next up then we have frame 2, and frame 2 is a B frame. And so frame 2 is going to use some parts of information from frame 1 and some from frame 4. B frames never use other B frames as a reference because the quality is generally pretty dodgy. So frame 3 is also a B frame, so it's going to use parts of frame 1 and parts of frame 4. That's a pity now because I spent an hour one day fixing all these arrows and I've obviously opened the wrong file. Frame 4 then is a P frame, and that's just going to use information, parts of information from frame 1. So when it comes to MPEG, you've got all these dependencies between the frames. So frame 2 is using parts of frame 1 and parts of frame 4. Frame 3 is using parts of frame 1 and parts of frame 4. And frame 4 is just using parts of frame 1. Frame 5 will use parts of frame 4 and parts of frame 7 up there. And frame 7 will use parts of frame 4. So the P frames only use past I or P frames as their references. And B frames use a past I or P frame and a future I or P frame. And that poses an interesting problem then for the transmitter and the receiver and how they conduct their business. So if we're transmitting a sequence of frames from A to B, the transmitter will say, okay, here's frame 1. And the receiver's yip-de-doo, thanks for that. Next up then, the transmitter sends frame 2. And it says to the receiver gets the instructions and it says, okay, now to make frame 2, take these parts of frame 1 and these parts of frame 4. And the receiver's like, duh, I don't have frame 4. So it can't be done. So what has to happen is that the frames have to be transmitted in an order that's different from the order in which they would naturally be displayed. And I can see the pain on some of your faces now. So we send frame 1. Then we have to send frame 4 next. And only once the receiver has both frame 1 and frame 4 does it make sense to send the instructions for making frame 2. So they have to be sent in that order. And then we can send frame 3. Because frame 4 uses parts of frame 1, so that's okay. Frame 2 uses parts of frame 1 and parts from frame 4. And frame 3 uses parts from frame 1 and parts from frame 4. But you can't make 2 until you have 4. And so next up then is what? 7. And then we get 5 and 6 and then so on. So frames end up being transmitted in an order that's different from the order of display, which is a bit of a head wreck, I think. There's also then problems with errors and noise and stuff. So let's say, for example, you're watching Sky and a bird hits your dish or something and you lose a frame. Just one frame. That can have some big consequences though, because that frame is required by, that's 1, 2, 3, 4, say there. That frame 4 there is required by frame 2. Frame 2 needs information from frame 4 in order to be built. And so does frame 3 needs information from frame 4. Furthermore, this frame here also needs information from that, as does that and that. So missing just one frame can have consequences for all of the other frames that depend on that. So compressed video isn't especially tolerant of loss. If you lose a bit of video, you can have some problems. Which of course is one of the reasons why we start all over again every so often. You'll notice if you're watching terrestrial television, if there's a problem, you see the blocks. You'll actually see some of the blocks go dodgy, and then a second later they'll maybe come back. If you're very sharp, you'll actually see that it's trying to construct the current frame from broken information, and you'll see it'll be like sort of a broken jigsaw with things being stuck down in the wrong place. But it only lasts for about a very short time, because then when the signal comes back, the next iframe comes along. It's okay, right? We're starting with a clean slate. For streaming video, you can code it in such a way that if the signal quality degrades, if the bandwidth drops, you might drop to a lower stream, or you might code the stream in layers so that you have like low quality and then some more information to turn that into higher quality and some more information to turn that into higher quality. You don't get that so much though. It's quite sophisticated to do. When you code video poorly, just as you see the blocks in JPEG, when you code JPEG poorly, you'll start to see the blocks in video. Once you understand how motion compensation is working, I find it very frustrating now that I see some parts of the image moving and some parts not. So if the camera's panning across from left to right, some of the blocks won't move at the same time as all the others. So I may have ruined your viewing pleasure now. We'll see next time you look at some digital video. It's actually very obvious to see once you know how it works. And if you see an explosion, I'd say you're not watching high definition and you're just in regular sky or something, and you see an explosion, or the opening sequence of some sci-fi shows, you just see blocks all over the shop. And I think for a long time, I don't know if it was Chorus or for Sky, but I don't know which was to blame, whether Sky was sending a poor signal to Chorus or Chorus was compressing it down even more. But you just could see the blocks everywhere when there was any explosion or going to warp or a fire or anything like that. So, any questions on that? It is quite it's quite complex, I think. It's very, very clever. I mean, you have to take your hats off to the people that thought all this up. Now, you probably know more about digital video now than most people. If you want to know more, I can tell you more about, not today obviously and not in class, but this process here of the bit where you go looking for the previous frame. Sorry, where you go looking for the missing block. Right? The part here where you have the current frame, you have a block in the current frame, and you want to find it somewhere in the previous frame. That's quite time consuming. That's what makes video compression asymmetrical. So JPEG is symmetrical. The amount of effort it takes to compress an image is the exact same as the amount of effort it takes to decompress an image. If it takes your machine, half a second to compress a JPEG, it'll take it half a second to decompress it. Video is asymmetrical. It can take hours to compress a movie that's going to play back in real time. And that's because of this looking for the blocks. So I did my master's in that, so I can tell you all about that. But only if you want me to. Okay? Any questions? Grand, we'll leave it there so.